Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we are talking about the first and last section of Unit 7. As a reminder, we did not start off with 7.1, we started off with 7.3. So, if you are here watching these videos after the fact, start with 7.3, work your way up, and then start over again. 7.1 is about something called inverse variation. And it's a great way to wrap up this unit because it really wraps up why we're doing what we're doing. So imagine this situation. You're throwing your best friend a surprise birthday party, and you're in charge of handling the food. Well, you figure that no party is complete without cookies, so you make them yourself. But you want to make sure that everybody at the party can take 3 cookies. I want you to try to write a function where x represents the number of people at the party and y represents the total number of cookies you need to make. Now, this is something I'm going to leave to you to try on your own, and then we'll talk about it in a little bit. But before then, I want to give you the other set of instructions as well. Cake. You also decide that no party is complete without cake, so you order a large circular cake from the local bakery. While you don't know the exact number of people that are showing up, you know that you can simply cut that cake into that many slices. So if 4 people show up, you can cut it into fourths. If 8 people show up, you can cut it into eighths. Write a function where x represents the number of people that show up, and y represents the amount of cake each person will receive. So try to make 2 equations like this. It shouldn't take us too long, maybe only 30 seconds to a minute. Pause the video and try it out. So hopefully when we're looking at the cookies one, we see that we could write an equation where y equals something. The number of cookies that we need to make should be equal to the number of cookies each person gets times how many people there are. So 3x. 3 cookies per person gives us y, our total. Now, if we were to look over here at the cake, though, things are a little bit different. In fact, it's a little bit trickier. Once again, y is going to be the amount of cake each person will receive. Here's the deal, though. If we have a lot of people, we get a little cake each. If we have little people, we get a lot of cake each. We may have realized that we have to write this as a fraction. 1 cake divided by how many people there are will tell us how much cake each person gets. I mean, think about it. 1 cake divided by 3 people is 1/3. You get 1/3 of a cake each. 1 cake divided by 20 people, you get 1/20th of a cake each. So, as we explain these two, we can in words write this out. For cookies, the more people that come to the party, we could say, the more cookies we need to make. The more cookies we need to make. Love it. We can also do the same thing over on this side. But this time, the more people that come to the party, we say the less cake each person gets. Kind of interesting. With cookies, we can say that we just have to make more and more cookies with more people. With the cake, we can then say, instead, less cake each person gets, the more people come to the party, the less cake each person gets. This is the entire premise of the lesson today. Direct and inverse variation. So, when we say direct and inverse variation, we're just talking about how x and y relate to each other. As one increases, does the other one also increase, like our cookie situation? As the number of people goes up, the number of cookies we need goes up? Or does the other decrease? As the number of people goes up, the amount of cake each person gets goes down. think about all the different things that could be a direct or an inverse relationship. I mean, the speed of your car and the distance you travel is a direct relationship. The number of miles away from the moon an astronaut is, and how far from the Earth they are, I mixed that up. How close somebody is to the moon and how close somebody is to the Earth is inverse. So if you get closer to the moon on a rocket ship, you're getting further from the Earth. Direct variation happens when if one decreases, the other increases. A is something called the constant of variation, and it can be any non-zero number. So yeah, the number of miles you drive and the number of hours it takes to arrive at your destination would be direct variation. Indirect variation is what happens when, as one quantity increases, the other one does the opposite. So like when x goes up, y goes down, because it's in a fraction like this. Down here, we see that this would be like the amount of homework we have and the amount of free time we have. I mean, think about it. As you have more homework, the amount of free time you have goes down. The less homework you have, the amount of free time you have goes up. So keep this in mind as we take a look at the following situations. We have to classify the following as direct variation, inverse variation, or neither. Remember, direct variation is when y equals some constant times x. Inverse variation is y equals some constant divided by x. It can also be neither. Let's take a look here. The number of fish in a fish tank versus the amount of space required in a tank. As one of them goes up, does the other one go down, or does it also go up? Well, the more fish we have in a fish tank, the more space we also need in the tank. So we would say this is direct, for instance. Let's take a look at part B. Y equals 7x. Since we know that direct variation is the one where it goes y equals some number times x, this is already solved for us. This is direct. What do we think about C? Is there a way to get y equals some number times x, or y equals some number divided by x? Unfortunately for us, there is no way to get it in either of those forms. We say neither. This is neither direct nor inverse. It can only be y equals some number times x, or y equals some number divided by x. What about in part D? Okay, well this one's a little interesting. We want to get y by itself, so it can be y equals something. So how do we do that? To get y by itself in this case, we would have to divide both sides by x, giving us y equals 9 over x. And this one here is inverse variation. This is inverse, because it's y equals some number divided by x. For E, we're also going to have to do some math to figure it out, but we know that to get y by itself, don't we just have to multiply both sides by 2? Because 2 and 2 cancel out, 3x times 2 is going to give us 6x. This is direct. Your running speed and the time it takes to run a mile. As one goes up, does the other go down, or does it go up with it? Well, if you have more running speed, the time it takes you to run a mile goes down. You have a shorter mile time. So this is an inverse relationship. The main idea behind this whole section is just picking out when something is direct, when something is inverse. Now, sometimes we're not given an equation. Sometimes we might just be given a bunch of points. And we have to compare these points and somehow decide, okay, what's the relationship here? So here we go. To tell if it's direct, inverse, or neither based on a table, we have to compare all the values of x times y and x divided by y. If x times y is constant, it means it's direct variation. If x divided by y is constant, that means it's inverse. So let's take a look. Here, we should do x times y and x divided by y to see what happens. Again, we want to test it out and see if either of them works. If x times y works, we're good, we've got direct. If x divided by y works, we're good, we have inverse. If it's neither, we say neither. So our first x times y is going to be 1 times 60, which is 60. Our next one is 2 times 30, which is 60. The next one is 3 times 20, which is 60. And 4 times 15, which is 60. Right off the bat, we've found out that this is going to be a direct variation because x times y is constant. We would say this is direct. Just to show you how you would check inverse, you would do it the same way. X divided by y, or 1 over 60, is just 1 over 60. 2 over 30 can be simplified to 1 over 15, so already we're not doing inverse. We have 3 over 20, and 4 over 15. None of these are the same. It's not constant. So what about B? I'd like you to try out letter B. See if this is direct, inverse, or neither. Pause the video and try and see if you can figure it out. What do we think? As we set up our x times y's and x divided by y's, we might start to see a little bit of a pattern. So, our first x times y is 2, because 1 times 2 is 2. 2 times 4 is 8, and already, it's not direct. Let's move over to inverse. 1 divided by 2 is 1/2. 2 divided by 4 is 1/2. Okay, we're starting to see a pattern. 3 divided by 8 is... Oh, that's not 1/2. 3 divided by 8 is just 3 over 8. And 4 divided by 16 isn't 1/2 either. It's 1/4. So even though it looks like there was a pattern here, this is also not inverse. We would say that our first one is direct. Our second one is neither. All right, let's take a look at the next ones. Of course, it wouldn't be a lesson if we didn't have to write equations and make equations as well. So we now know two formulas. Y equals ax for direct, and y equals a over x for inverse, where again, a is just some whole number. Well, it doesn't even be a whole number, it can be a constant too. However, there is a third case other than neither. Sometimes a quantity varies directly with the product of two or more quantities. This is called joint variation. Let me give you an example. The performance of a team, like a soccer team, and the performance of its best player, second best player, third best player, fourth best player, so on and so forth, is a joint variation. Because if even one of them does a little bit better, the whole team does a little bit better. If all of them do a little bit better, the whole team still does a little bit better. If one of them does worse, the whole team does a little bit worse. So joint variation is where a bunch of different quantities all impact directly your result. So let's take a look at example 3. We're now looking to write an equation using these variations, plug in the values we know, and then solve for a, our constant of variation. So in example 3, we're trying to write an equation that relates x and y. And the two values we know are this. First, we should write the equation, then we can use this information they give us. So, the variables x and y vary inversely, and y equals 4 when x equals 3. Let's see what we can do with this. So if x and y vary inversely, we know that y is going to equal a over x. Now, that y equals 4 when x equals 3 tells us that we can plug those two in to find our constant of variation, a. So y is 4. 4 equals a over 3. We now just have to get a by itself to solve for it. To do that, we multiply both sides by 3, and we get 12 equals a. So now we have our equation, our function, our inverse variation. Y equals 12 over x is our equation. Now, we're asked to find y when x equals 4 and z equals 3. We don't have a z in this problem, so it doesn't really matter, but we are trying to find what y is when x is negative 4. Well, to do that, we just plug it in. Y equals 12 over, we're plugging in this negative 4, so it's going to be 12 over negative 4. 12 over negative 4 is just negative 3. So y equals negative 3. That's going to be our answer when x equals negative 4. For part B, we have variables that jointly vary. The variables x, y, and z vary jointly. So we should write y equals ax, because that's the formula for joint variation. Again, we need to solve for our a, our constant of variation. So let's plug in the values they tell us here. Y equals 2, x equals 4, and z equals 2. So, y equals 2. We have our missing a value. X equals 4. And z equals 2. Well, this simplifies down a little bit, where we can just say that 2 equals 8a. And how do we get a by itself? Well, of course, we have to divide both sides by 8. 2 divided by 8 is 1/4, so 1/4 equals a. We found our equation. Y equals 1/4 x z is our equation. But now it asks us to find y when x equals negative 4 again, and z equals 3. So let's plug them in and find y. Y equals 1/4 times negative 4 times 3. Negative 4 times 3 is negative 12, and 1/4 of that is, oh, would you look at that, y is negative 3 once again. That was not intentional. Y equals negative 3. So you might see a problem like this, where you're asked, write an equation that relates x and y, where you'll have to solve for a, and also find y when x is this, or z is this, or whatever may have you. We've got two more examples that we're going to talk about that we might see from this section. Sometimes we have to write an equation to represent the relationship. Oftentimes it's pretty easy. Like if y varies inversely with x, we know that we can write y equals some number a over x and call it a day. What if y varies inversely with the square of x? Not the square root, but the square. Okay, makes it a little bit trickier, but we would have y equals a over x squared, right? Okay, good so far. But what if y varies directly with z and inversely with x? Ho, now we've got a situation. We're still going to have y equals, but it varies directly with z. So we know that we're going to have a times z in there. But it also varies inversely with x. So what do we do to show both of them? Well, we recognize that an inverse relationship with x just means that x should be in the denominator of a fraction. This shows that y inverse directly with z, since it's y equals az, and since it's over x, it varies inversely with x. Now we're going to start getting into some trickier ones. We're not using x and y's anymore. We're using actual physics formulas. So if you're taking physics right now, you might see some of these. R is inversely proportional to S, which is another way of saying it varies inversely, and is directly proportional to the square of t. If R is inversely proportional to S, we know we can write it as R equals A over S. But it's also directly proportional to the square of t. So it should be A times t squared. R equals AT squared over S. What about this one? G is jointly proportional to X and Z and varies inversely with W and Y. Ho! We need to recall that joint variation is just direct variation with multiple things. So we would write this as A times X times Z, since those all vary directly. And if we're inversely relating to W and Y, those will go on the bottom. This last one is an actual physics application. The power P generated for a translational motion varies jointly with the acting force F over a distance d, and inversely with the time t taken to perform the action. Now this is getting brain melting. This is getting a little bit long, but let me explain. The power that is generated for translational motion, so like the power to slide the pen across the table, varies directly with the acting force F, so how much force I'm putting behind it, over a distance d. That just means the more force I give it, or the more distance we go, we say that that is more power. And inversely with the time t taken to perform the action. It takes a lot more power to do it in less time than it does to do it in a lot of time. So when we write this, we keep in mind that P is jointly proportional with F and D. But it's inversely proportional to the time taken, meaning the longer time, the less power. The more power, the less time. This is how we write it. These take practice, so when we do the big ideas, try some of these out. You might surprise yourself. Here's the last question, and this is a thinking problem. I had to give you some hard ones for such a quick lesson. The area of a rectangle is 64 square inches. Write a function y describing the height of the rectangle with relation to x, the width. Then, use a function to generate the list of all possible integer dimensions and graph that function. What on earth does this mean? Let's start with the first question. Write a function y describing the height of the rectangle with relation to x, the width. Well, we know the area of a rectangle is base times height, or x times y. But do we want to have x and y on the same side? Not really. It says we want to write a function y describing this. So how do we get y by itself? Well, those keen among us might know that we should divide the x out. If we divide by x, y will be all by itself. We end up with a over x equals y. And in fact, we know what a is. We don't need to solve for this. We know that a is 64 inches squared. So our function is y equals 64 over x. This is our function. And what type of variation is it? It's inverse variation. So this means that as x, our width grows longer, our height is actually going to get smaller. And as we get taller of a rectangle, to stay at the same area, our width has to get smaller. Now it asks us to use this function to generate a table of all possible integer dimensions. Everybody, integer means whole numbers, positive and negative. As we take a look at this, we need to generate a table of every single x and y, positive and negative, that can make this work. How? How do we even do such a thing? Well, it's not as hard as you might think if we have our function here. I mean, think about it for a second. Let's say I plugged in 1 for x. If x was 1, 64 over 1 is an integer. 64 over 1 is just 64. So we found one of them already. Let's try the next one, 2. Can 64 be divided by 2 and get us an integer? Yeah, 64 divided by 2 is a whole number. It's 32. Can x be 3? Can 64 divided by 3 give us a whole number? No, 64 cannot be divided by 3. 60 can, 63 can, but not 64. So we skip x equals 3. 3 is not going to be a possible integer width. Do we start to get the picture? In a second, I'm going to have you finish up this table on your own, but I also want to show you that it works backwards too in the negatives. So, if x was negative 1, what would y be? Well, 64 over negative 1 is negative 64. You might start to see a bit of a pattern form. So I've split this table up into positives and negatives. Try to see if you can find all of the integer combinations that work for x and y. Pause the video and try it out. How'd we do? Hopefully we started to see that the only ways this is going to work is if x is a factor of 64. So what are all the factors of 64? Well, 4 works. We know that 64 can also be divided by 8. We know that 64 can also be divided by 16 and 32 and by itself, 64. If we plug in 4, we get 16. If we plug in 8, we get in another 8. If we plug in 16, we get 4. If we plug in 32, we get 2. Plug in 64, we get 1. And we start to see that there's a pattern here. These lists are just flipped versions of each other. So when we go into the negatives with things like negative 2, negative 4, negative 8, negative 16, negative 32, and negative 64, it works the same way. We get negative 1, negative 2, negative 4, negative 8, negative 16, negative 32, and we already did negative 64. We have 14 points that we can plot on our graph. And once we do that, we're good to go. Now, this graph obviously can't fit 64 numbers, so we'll have to scale our graph a little bit. How's about we count up by 8s? So 8, 16, 24, 32, 40, 48, 56, 64. And we'll have all the other parts of our graph be the same thing. I'm not going to label all of the axes, you technically should, but we know that this is going to be scaling by 8s. I'll at least jot down the y-axis here. 8, 16, 24, 32, 40, 48, 56, and 64. And I can barely read that. I'm trying to write small because we're going to have a lot of dots on here. Let's start by graphing the positive ones because that'll be the easiest. At an x value of 1, our y value is all the way up at 64, so right here. At an x value of 2, it goes all the way down to 32, so like right around here. At 3, or we don't have one for 3, but we have one for 4, it's at 16, so it'll be like this. Right here in the middle. At 8, it's just 8, so that's right there. And we can keep going with this on and on and on. So for 32, it'd be like right here. 64 would be right here. We might start to notice something. What shape does this form? Oops, that was a little bit off. We're starting to see that this forms a hyperbola. Let's graph the other points just to make sure that's exactly what happens. So, if we plotted the negatives, negative 64, negative 1 is a point, so like right here. Negative 32, negative 2 is a point. Negative 16 and negative 4 is a point, so that'll be like right here. Of course, we have negative 8, negative 8. We've got the next one is negative 4, negative 16, negative 2, negative 32, negative 1, negative 64. Yes, it is a hyperbola. This is our resulting graph. We have come full circle. The reason for us doing all this rational function stuff, for dealing with hyperbolas, is because rational functions with an x in the denominator portray inverse variation. Because anytime you have two quantities that vary inversely with each other, like the sides of a rectangle, such as the amount of cake each person gets at a party, such as the amount of homework you have and the amount of free time you have, the running speed and the time it takes to run a mile, all of this has been what we've been talking about all along. Anytime you have one thing goes up and one thing goes down, you've got this hyperbola. And that's why it is so critical for us to learn this. What a conclusion to this unit. Thank you so much, everybody. Have a great rest of your day.